In this lesson, we're going to just have a brief introduction into what is called differential equations. And you see some stuff on the board, but don't worry about that yet. A differential equation is just an equation that contains an unknown function and one or more of its derivatives. So I have a differential equation up here. Now it's because we have an unknown function, y, and in this case, the second derivative of y with respect to x. So this is just one equation where we don't know the function. The basic task is find the function that satisfies those conditions, or in this case, this one condition. Three things to know, three ways to kind of classify a differential equation. The first one is the type of differential equation. We have ordinary differential equations, also known as, if you Google this, ODEs, or partial differential equations. Those are PDEs. For our purposes, we will not study partial at all. If you maybe in your, if you're taking a physics class, you might see partial differential equations on a high school level, but outside of that, you'll see much more of it in college. So ordinary differential equations will be our major undertaking. The second thing is the order of a differential equation. And the order is the highest order derivative in the equation. So in this case, this thing is order 2 because the highest order derivative we have is 2. And then the degree is the exponent of the highest power of the highest order derivative. I'm going to say that again. The exponent of the highest power of the highest order derivative. So in this case, technically, this is all raised to the first. So we would say this is a degree 1 differential equation because this is the highest order derivative that's here, and the power of that is 1. So this thing would then be an ordinary differential equation, order 2, degree 1. Okay, and you might look at that and say, I have no idea how to solve that thing. So let's just briefly, let me put up a solution to this, and then we'll briefly discuss why it's a solution. Okay, that function, these where C1 and C2 are just real numbered constants, this is a solution to this differential equation. And if you're thinking, I have no idea how that works, well, let's look at its derivative. First of all, it might be useful for some of you to think of this as y double prime. Sorry, that might be a little close together. Y double prime plus y equals 0. So what I'm going to do down here is calculate y prime. And y prime will be, we have a constant times cosine, that'll be negative constant times sine plus our constant times cosine. And of course, our differential equation involves the second derivative. So again, these two are the same. We could calculate the second derivative. That will be negative C1 cosine of x minus C2 sine of x. And now if we take that, remembering that these are just some constant value, whatever they are, they could be positive, negative, whatever. And if we take those values and we then add y to it, so if you look at the original, it says y double prime plus y. So this is y double prime plus, I'm going to put y right there. And the claim is that that equals 0. Well, our differential equation dictates that it equals 0, so better. And if we put y1 in here, it'll be C1, that's a C, you'll have to trust me. C1 cos x plus C2 sine x. If you're wondering where I'm getting this from, it's right there. That's y. And again, if you're wondering why I'm doing y, it's because the differential equation mandated that fact. So now you can see negative c1 cos x plus negative c2. Oh, that definitely does equal 0. So you might think to yourself, well, yeah, okay, fine, man. I guess it works, but where'd you get that from? First thing is, the scope of our course will not actually cover second order differential equations. So this right here, just by being a second derivative, immediately we're kind of exempted from studying that. I just wanted to use it as a tool to show you how solutions to differential equations work. So anyway, we're only dealing with order 1 in IB. Okay, so let me put up a simple first order differential equation. So y prime equals x cubed. That's actually one that's in the book. Let's do 5x to the 8th. Okay, if that's the first derivative, y prime, you can think of this as dy dx, right? So one thing you could do is simply look at this and say, oh, if that's the derivative, I know what the antiderivative is. It is x to the 9th and then 5/9 plus c, right? This would be the antiderivative of that. So that actually will work as our function. Now, this is what we call a family of functions because 5/9 x to the 9th makes a certain curve, and plus c would just shift it up and down because we don't really know what that constant is because we're not given any other condition. Now, if you thought about it as dy dx, and we'll get much more into this when we talk about separation of variables, but y prime is dy dx, and we already really know that this is going to be fine as a solution because multiply 9 times 5/9, you get 5x to the 8th. Derivative of that is 0, of course, so that will do the trick. But with separation of variables, effectively, what we'll do is we'll say this. We'll multiply the dx over 5x to the 8th dx. And now what we'll do is actually just integrate both sides. And this gets into an idea of separation of variables, so you'll deal more with that in a while. The integral of 1 dy, with respect to y, is y, and the integral of that is, of course, 5/9 x to the 9th plus c. And you might think to yourself, boy, you know, this is all very long-winded compared to just doing that. And I understand that, but we're trying to lay a little bit of groundwork for separation of variables. Okay, so again, just to classify this thing so that you have the vocabulary down, not that it's a hugely important thing, but it's nice to know. First of all, this is ordinary because we didn't have any partial derivatives in it, and it's order 1, and the degree on it, the highest power of this derivative is 1 as well. So this is just about as easy as a differential equation gets. Now, let's say you could have something like dy dx equals (3x squared). And also, you could be told that y of 2 is 12. So now using these two, instead of finding a family of functions that works, we can actually find the specific function that satisfies both of these conditions. So we could even actually, let's make it y of 0 equals 12. So now this would be called like an initial value problem because I'm giving you an initial value. These are obviously useful for anything physics related, thinking position, velocity, acceleration type problems, which you've already studied. So this might be, you know, the initial position is 12, and here this thing would describe velocity. So these things have very far-reaching applications, but we'll only be treating very simple forms of them. So the first thing is, we could clearly see that y will equal x cubed plus some constant value, because 3x squared would be its derivative, and derivative of y with respect to x is, of course, dy dx. Also, this problem could have been stated as y prime equals 3x squared. So, let me get rid of that though. And now, y of 0, this is typical notation for differential equations. It just means that when you plug 0 into the original function, y, and when you plug 0 into x, you get 12, which tells me that y of 0 is equal to 0 cubed plus c. Y of 0 we know is 12, is equal to 0 cubed plus c. Therefore, 12 is equal to c. So now we know the specific solution would be y equals x cubed plus 12. And hopefully you're thinking to yourself, we've already done this. We've already taken functions, forget that it's a derivative, we've already taken functions, found their antiderivatives, and used a specific condition to find what function satisfies all of those conditions. What will happen in the future with differential equations is it'll just get more complicated. You know, instead of having a function that you can easily unravel and find the antiderivative, you might have a function like the first one I put up there, the order 2 differential equation that I put up there with the sines and the cosines. In functions like that, you have to employ different techniques. And a lot of differential equations is recognizing a certain form of something and then just reaching out and grabbing the right tool for that and the right technique for it and then applying it. By the way, you might have noticed that I changed this condition from y of 2 or 3 or whatever it was to y of 0. If this was y of 2, we would have done the same exact thing. We would have just plugged 2 in here and we would have found a different c value. I changed it just so that you could, you know, just so that we have done a specific initial value question. Okay, so that just about does it. Hopefully you understand what a differential equation is. And a differential equation basically is just an equation involving the derivative of an unknown function. You can hopefully have some feel for the vocabulary and then for some simplistic examples that we've done here. And more difficult examples, you can at least see how it works even if you don't know why the particular solution works.